And we're back. Pay no attention to the fact that I seem a little sweatier and I'm wearing a different shirt. We just had graduation postponed due to lightning. Don't mess around with lightning, kids. Get in a car or a safe building, that sort of thing. Okay, back to what we're actually taking a look at. Last question on the released free response for the 2026 APC Mechanics exam. So this one's the QQT, Qualitative Quantitative Translation. This one follows a pretty standard form across all the physics exams. It is worth 8 points. Recommended time is usually about 15 minutes, sometimes 20 minutes. I'd say this one's much more of a 15 minutes. So we've seen some very challenging questions on the other parts of the exam. This one has some challenge to it, but hopefully this one did not throw you for too much of a loop. I really like this one, not for being excessively challenging, which is one thing that I like, but I like this one just because I think it's very approachable and definitely just a good question overall. Unicycle is set up on a stand. Basically, they've got the setup initially such that the unicycle is like a standing bike. You could imagine like at a gym or something, except it's just got the one wheel to simplify your analysis, and then you don't have to worry about a gear train or anything like that. Unicycle is placed on a stand such that the wheel does not touch the ground. The rotational inertia of the wheel about the axle is I sub W. One end of the crank arm can be attached to the wheel as shown in the side view. So we've got basically unicycle here, we've got a pedal here that we can actually turn around. In scenarios 1 and 2, crank arms of different lengths are connected to the wheel. In each scenario, the wheel is initially at rest. A force of magnitude F is then exerted on the end of each crank arm. The direction of the force remains perpendicular to the crank arm at all times. As a side note, you can even see here they almost have what appears to be a little pedal. Imagine like a bike, you have the pedal that can rotate so that your foot can comfortably adjust angle as needed. That's kind of what we're looking at here. Okay, let's see. But it is useful that it remains perpendicular at all times. We'll talk about that in just a moment. The mass of each crank arm is negligible. The scenarios differ as described. Scenario 1, the length of the crank arm is L1. The angular speed of the wheel immediately after the crank arm has been turned through one rotation is omega 1. Scenario 2, the crank arm is L2, which is greater than L1, and then omega 2 is the same thing as, same setup as omega 1. Okay, part A, indicate whether omega 2 is greater than, less than, or equal to omega 1 by writing one of the following. So we're going to identify the relationship first, and then we have to justify our answer. And here's the key. With a QQT, they say it here, your justification may reference equations, but must include conceptual reasoning beyond algebraic solutions. I'll reiterate this if I haven't said it clearly before. The instruction word justify means use your words. You can have equations or something to back it up, but if you don't have words that are explaining what those equations are saying, then you're throwing away points, is my understanding on this. They are explicitly telling you, while you can make reference to those things, it's your words that matter. So make certain that you're given enough description of the key ideas here. We're going to go through that in just a moment. This is pretty much, part A is pretty much always 3 points, and you'll be doing something similar to this on pretty much all of them. Part B is going to be a derive that is pretty common. Usually it's a derive related to part A. If you're dealing with the algebra-based AP1 or AP2 exams, usually part C is then you have to compare the two, making reference to your functional dependence in part B. We'll talk a little bit about that, but we'll see if it actually has an application here. On the mechanics and the E&M exam, they have a higher likelihood of part C being where they're going to change things out a little bit and ask you to do something, once again, either justify in this case, or sometimes maybe do a little bit more deriving. Usually it's a bit more challenging than what's on the AP1 or the AP2 exams, at least from what we've seen thus far. Okay, going back to what we're looking at. Okay, a bunch of different ways to apply this. We're spinning a thing up. We could apply Newton's second law in rotational form and then connect that to kinematics. That is a perfectly good way of doing it. Our clues on that are Newton's second law, because we're speeding something up, it has a non-zero acceleration, be that linear or rotational. They've told us that it's the same force applied to both of them. So forces and accelerations, great, but an important part of this is that we're going through one complete rotation. That's in this case, angular displacement, but we could also convert that over to a linear displacement for comparison's sake. But while that draws my attention, other things that could be applied is when I'm looking at speeding things up, I could be changing its angular momentum. I do that by applying a force over a time, and that's my clue that I probably don't want to use angular momentum for this question. If you're studying for another exam, which you might be, keep an eye out. If you have forces and times, well, you might look at impulse, but we can eliminate that. I don't want to say eliminate. You can do it that way, but you're going to have more steps. The thing that jumps out to me, though, is forces and a displacement, angular or otherwise, my brain immediately goes to work. And as I've said to many of my students before, work energy is a great way to solve problems if you can. The biggest limitations for energy are it doesn't tell you time. Well, we're not depending on time. They're not even asking about time on this. So that is not a disadvantage on this question. And it can't tell you direction, but we're not having to worry about the direction of this. We're just looking at the overall effect. In fact, when we're talking about omega, a great place that shows up is our rotational kinetic energy equation. And that just narrows this in that I think your best approach is work energy. Now, you could also solve this with Newton's second law and then kinematics, but you'd have to bring in some rotational form. That being said, we're going to solve this from the rotational work energy viewpoint because I believe that's the strongest approach, but I wanted to talk about your clues that give you an idea as to why that would be a good approach. Okay, so on this, the biggest things that I would say are this, the things that we need to think about. Remember, you can have equations, you can reference equations, but you got to use your words. So on this, I could say part A, here's what I'm thinking. The key equations that I'm looking for are work is equal to my change in energy. Well, the energy that we're dealing with, because this isn't going uphill, has no springs or anything like that, is all kinetic energy, which is what it has on the AP exam equation sheet anyway, that they have our change in kinetic energy. This is the work kinetic energy theorem. They default to that because it applies to technically any object, regardless of how you define the system, whereas broader aspects of energy depend on defined system. Okay. Plug for that out of the way, especially in case you're a student that is not mine and is not used to seeing it written this way. Here's the work energy, and I think on the AP exam, they simply have it as delta K. That being said, our work. Work can be a force applied over a displacement times cosine of the angle between them, or F dot delta x or F dot dx integrated as the case may be. This is for linear work, which you could actually apply and you'll get the same outcome, but it might be a little bit more confusing. What I really like is this, that our work for a rotational viewpoint is technically our torque times delta theta. Once again, force becomes torque. Delta x, a linear displacement, becomes an angular displacement. Technically, there are angles that would come into this, but that's where that thing that they said about how the force is always perpendicular to the crank arm, the lever arm, that helps keep that the same, where we won't have to worry about the angular part of this. So our work is going to be done by torque applied around delta theta, and that's going to be equal to our final kinetic energy, which is 1/2 IW omega squared. I'm just going to say omega. And then minus 0, because our initial kinetic energy was 0. It said we started from rest. Now, delta theta we know is the same for both scenarios. I is the same for both scenarios, and we're trying to find out about omega, so there must be a difference somewhere else. In fact, it's in the torque. We have the same force, but remember, torque is equal to our force times a lever arm, or crank arm, or radial vector, times sine of the angle between them. Once again, this is always pushing directly into it, so the sign just evaluates over to 1. And then for students that are not mine, you might see this as RF, where R is a radial vector. We use a reference to the engineering standard, which is the lever arm when you're dealing with forces and torques. In this case, what that gets me is this. I get that F times my lever arm, which is the length of the crankshaft, which they identified as L, delta theta, equals 1/2 IW, and then omega squared. This is actually getting us set up for part B, but this is what I'm thinking through in my mind to set things up. None of this will get you any credit on part A, because once again, I'm not using my words. But that doesn't mean that it's not useful. So here's where I can see my relationship. Here's what I'm going to do. Force is the same. Delta theta is the same, because we push with the same force, we push through one rotation, and so delta theta is the same. Delta x is not necessarily the same, but delta theta is because it's one rotation. The rotational inertia is the same. So the only things that we have are L, and that is relating to omega. So if we had L1, that's going to be related to omega 1 squared. L2, omega 2 squared. And here's the key thing that we're looking for, especially in a QQT. If you hadn't already pieced it together, here's what we got. The amount of energy, the work we do, is our torque times delta theta. Well, we've got the same delta theta, and one of these, they both have the same force, so the one with a longer arm has a greater torque and therefore will do more work. That gives more energy, and more energy going into here with the same rotational inertia means it must be spinning faster. So now I can draw my conclusion. Since L2 is greater than L1, and these relationships are here, whether I worked through it mathematically, semi-mathematically like this, which will pay off in part B, or if I just reason my way through it, this is perfectly fine too. This leads me to the conclusion that omega 2 is greater than omega 1. In this case, key things that I've seen students overlook when they're doing justifications or justify. And that's why I recommend setting up the thing that you've got here so that you can try and check everything off. I would start off by telling us everything that stays the same. Because F, not L, but delta theta, and IW are the same for both, the work done, or energy added, done, or energy added. I like to phrase it a couple ways. Don't go too far out of your way, but the more you can try and get across the idea, the better, without cutting into the time that you need to get the problem done. The work done, or energy added, is greater for the longer crank arm. In this case, that carries over. Basically, L is tying into that. We're identifying that the longer crank arm is going to result in more work being done, which is a true statement. That means we have more energy added. Therefore, the wheel in scenario 2 will spin faster, having a longer crank arm, or longer arm, more energy added, and same rotational inertia. Now, all the key ideas are in words. Here's your way of describing it. It doesn't mean that you can't think in terms of equations, but here's where we're setting you up. Most people doing this are looking to go into STEM and engineering. One of the most important things that you need as a professional engineer or people working in STEM is not only can you solve the math, but you can understand it and you can explain it in a way that others can work with. So do not underestimate the importance of us asking you to do this. Okay, great. So on this, the key things that I had, I think from what I've seen, though this is a new kind of style of question, I've seen a lot of, I don't know if it would be this, but usually having something where you correctly identify omega 2 is greater than omega 1 and an attempt at a relevant justification. And I do say relevant on this. I like to give the example of, okay, if you said omega 2 is greater than omega 1 because the number 2 is greater than the number 1, so therefore this must be true. That's a justification, but it's not really a relevant one. It's not making reference to any physics or anything like that. Now, what we mean by attempt at a relevant justification, if you start talking about, say, for instance, I told you angular impulse. Maybe you all went through and said, hey, we have the same force being applied and it would be about the same time. It's not necessarily the same time is the problem with that. And that's why it wouldn't be a correct statement, but it's actually a relevant one. And it's not a bad one. It just doesn't necessarily apply to this. That would be one that would be a relevant justification. And it does not have to be correct. It just has to be reasonable, for want of a better term. That's one of the things that they've got kind of set up in this. So don't worry if you didn't get exactly what you were looking for there. If you didn't take the energy approach, once again, you could easily do this with Newton's second law. I'll try and incorporate that when I write up the grading rubric, my recommended grading rubric, or my predicted, that sort of thing. +1 for identifying, something like that, for identifying or addressing that, so IDing, we'll call it that, Some of the things that stay the same, that they have the same force, the same angular displacement, the same IW. Basically, we do need you to identify that a couple things are the same. At least from my experience, maybe they've gone lighter on that, but I would still recommend it. Just because one thing, like L is greater, that doesn't necessarily mean omega would be greater. It all depends on, in this case, the other things staying the same. If L were greater and I pushed less hard, if F were different, then we might have a very different outcome on this. So don't overlook identifying things that stay the same. Even if you just say, hey, F, delta theta, and I omega, they're all staying the same because we're one rotation, same force, that sort of thing. Okay, and then that L2 is greater than L1, something like that, identifying the change that they've introduced, and then +1 for connecting the length L to torque or work done, because those are the kind of the key things that they have listed there. In this case, because they tell you the force is the same and L is different, I would say that you're really going to have to address the torque either directly, explicitly, or if you have a really well written one, you might not necessarily even use the word torque, but if you're saying, hey, same force, longer L, we have more work done, or you could also do the work from a linear viewpoint. You can have the magnitude of the force and find your displacement, which would be around the outside edge. Well, the longer crankshaft would result in the circumference of a bigger circle. You could do it like that, and you'd never mention torque, but at the end, you would still make reference to the work done. So when I say this, the work done is really the key part of this, because that's what carries it over to the energy. Oh, I'm sorry. Maybe this actually kind of blends into that, because we do actually need one other thing. And because the work done is greater, come on board, that means that KE2 is greater than KE1, and therefore omega 2 is greater than omega 1. Remember, this is only a true statement because our rotational inertia is the same. I apologize, I'm a little scatterbrained right now. But these would be more or less the breakdown of the 3 points. I could see some of this being moved, maybe this up into here. It all depends on how they want to lay that out. But these would be the key things that you would actually have to address on that. Okay, let's see, B. And I've gotten ahead of myself. We had spent a little bit of time on that, but now on B, they want us to derive, and it will usually be deriving something related to this. Derive an expression for the angular speed omega 1 of the wheel in scenario 1 immediately after the crank arm has been turned through one rotation. So in this case, because they gave us 2 different scenarios, they're going to simplify it on us and say, look at just one of them, solve for the one, and then in part C, you could then extrapolate off of that after you see the relationship. Although in part C for us, they're going to change it up a little bit. Express your answer in terms of I, omega, F, L1, and physical constants as appropriate. Well, here's where me thinking this out and even doing some of my equations above ends up helping me out. Let me double check. Does it say begin your derivation by writing a fundamental physics principle or an equation from the reference sheet? Great. We already know where we're going with this. Work equals our change in kinetic energy. This is, if I'm not mistaken, what is on the AP equation sheet. Or you could also set up that your kinetic energy is equal to 1/2 I omega squared. This would be also an equation from the equation sheet so that we could start our derivation with that. In this case, I'm going to then expand my work, like we said before, where this becomes my torque times the length of the crankshaft. In this case, we're looking at scenario 1, so I'm going to do L1 equals 1/2 IW omega 1 squared. In this case, as a greater, I could see with work, we're expanding that out to, oh, no, not torque times L. I apologize. I wrote that badly. Bad, Sanchez. Okay, so that's delta theta. Again, brain a little melty. We've got that. That looks good. And then I can see that we're expanding this to be the angular definition of work. We're applying a torque over an angular displacement. I've replaced delta K with this. I'm seeing the final one. I know that this should be -0, especially for APC. If there's something that's 0, it can be helpful to put that in there so that we know for certain, but this should be perfectly fine that we can see, hey, it was 0, you dropped it. Moving forward, on this, our torque, like we said just a moment ago, is going to be FL1 times delta theta, and that will be equal to 1/2 W omega 1 squared. What is it I was aiming for? I think I'm almost done on this actually. Let's see. I want omega 1 equals some stuff in terms of F, L, and I omega and physical constants. Now delta theta is not something that's allowed in there, but I do know that it is one complete rotation, so I can actually replace that with 2 pi radians equals 1/2 I W omega 1 squared. At this point, I just solved for omega 1, so I'm going to multiply both sides by 2. I end up with 4FL1 times pi, I guess 4 pi FL1, you can write them in any order, divided by IW, and that's going to be equal to omega 1 squared. I can take my square root, and this should be our answer. I'm allowed to answer in terms of FL1, IW, and pi and 4 are just numbers. So here is our derivation. And again, this might have taken a little bit longer, but it can be very helpful in part A to kind of think through what your approach is. Sometimes, depending on your circumstance, maybe you jump to part B, do the derivation first, and then let that inform and set up your, oh, I see what I was doing. I was putting the energy over there. Sometimes a lot of students get much more comfortable applying the equations first, but we do want to build your ability to express that. Whether you start with equations or not is up to you, but we want you to be able to do these skills. Okay, so big things. Like usual, +1 for a multi-step derivation that begins with an equation from the equation sheet. I've done that. I did a replacement here. In this case, I'm pretty certain that we would have, more broadly, it would basically be for an appropriate setup that allows you to relate omega 1 and in particular L, because that's going to be the thing that they asked about in the first part. But for this specific one, if we're taking a work energy approach, then I would say the next one would probably be for an appropriate expression for the torque on being applied in scenario 1, being able to bring in F and L1 since those are key things that we need to answer in terms of. And then probably for this, because it is not a very difficult one, +1 for a correct answer. If this were a tougher derivation, which I've seen on some of the QQTs before, you wouldn't necessarily have to get the full answer. They might have something where it's like 1 point for correctly relating it to your change in kinetic energy. This one might also be for +1 for actually setting up work energy correctly and replacing things out. I'm just going to call it about the torque because to me, F and L1 are kind of the big things that you're trying to bring back in. But I can see it fluctuating a little bit. This will be worth 3 points. That much I'm pretty confident on. And then our last part, let's jump to the last part, part C. In scenario 3, the unicycle is placed on the ground such that the unicycle can move forward without the wheel slipping on the ground. So we have no kinetic friction that's eating up any energy. And here's the other reason why energy is just a really good way to go about most problems. Again, unless you need time or unless you need to know direction, energy is almost always a really good option. Oh, sorry, except one other, collisions. Collisions are bad for energy. Okay, so taking a look. Force of the same magnitude F is exerted on the end of the crank, L1, same as scenario 1. The direction of the force remains perpendicular. We're setting all this up the same way, but we've taken the unicycle off the stand. And now it can roll without slipping along the ground. So when I pedal, I'm riding the unicycle. Now, the important thing is my force is the same. My lever arm is the same, so my torque is the same. And once again, I am only doing one full angular rotation. Now, I keep going to torque and angular rotation because they've told us that we have the same angular rotation. The linear displacement is the circumference for the linear approach to work, and that one's not technically the same. Well, I guess it would be for this one, which is fine. The key thing on this is I'm still doing the same amount of work. We haven't changed the length of the crankshaft, we haven't changed the force, and I'm still doing one full rotation. In fact, we're in the middle of justify. Here's exactly what I would do. I would follow this up by saying part C, which is worth 2 points. I would say the following. Okay, we still have same force delta theta, and now the same lever arm. So the work done remains the same. I don't know for certain. You might actually write out that this is force, angular displacement, and then crank arm, just to be safe. Again, AP1 used to be very, very focused around using your words. I don't know how much that carries over with the new exam. you'd probably be fine with identifying them by the actual variables, but your words are very important here. So our work remains the same. So same energy. Okay, now for my students, I've asked you this question a bunch of different times, and for many other students, you've probably seen them too. We had the following where you have a ramp and you've got a block that can slide down with no friction. I am really, really getting tired right now. Versus a wheel that has to roll without slipping down. Which one gets to the bottom first? Well, it's the block without friction because all of its energy goes into translational kinetic energy. It doesn't have to put any into rotational. Well, the same thing comes into play here. We're now looking at omega 3 versus omega 1. Well, omega 3 has a unicycle that we put the same energy into, and it can spin, but it also has to move forward. Whereas on omega 1, it is still on its stand, and so all of the energy will go into rotational instead. Since omega is based on the amount of rotational energy, we have our answer. Omega 1 is greater than omega 3 because... My board is acting up, I apologize. Because same total energy, scenario 3, splits that into Ke rot, rotational, and Ke trans, translational. Scenario 1 only has Ke rot. So all energy goes into spinning. For 1. Therefore, omega 1 must be greater than omega 3. All right, I really do like this question. I might be hint using this on future exams, but here's how you break this down. I don't know because I haven't watched nearly as many of these for APC when they do something different. I know what this normally looks like for the AP1 exams, and sometimes they ask it in that format on APC. But you would have two different things, or 2 points on here. I think that it's likely going to be, once again, like we saw before, correctly identifying omega 1 is greater than omega 3, and an attempt at relevant justification. Once again, they're very careful about that so that you can't just have, because I feel like it. That's not a relevant justification. So try and tie something in with physics, even if you don't feel 100% about it. Definitely try something and make certain that it's related to physics if you can. And then the other point I would say for a complete and correct justification based on any reasonable approach, as long as it's correct. So I focused on the energy approach because I feel that that's one of the most versatile, but you could have also done this once again with dynamics and kinematics by looking at the torque being applied. It has the same rotational inertia. So the one with the greater torque has a greater angular acceleration. You have the same angular displacement, and so you could make those arguments as well. Okay, but here is what I think is going on with question 4. Hopefully that was useful for you. Until next time.